Okay, so I'm starting the recording. Um, so tomorrow, as you know, you'll have a second midterm. The format is almost exactly like that of the first. So I've already written the exam. You will take it, if you're in a nearby time zone, you will take it at 11:30 tomorrow with your camera on so that I can try to proctor the exam effectively. If you're in a different time zone or a very far away time zone, then you'll have a window during which you can take the exam. It will once again be a 1-hour exam with an additional 10 minutes where you can upload your papers that you have produced to Gradescope. There will be a new Gradescope what's it called? There'll be a new Gradescope entry open and available to you. Yeah, and it should more or less shake out like it did last time. Any questions?
Are you able to speak to whether it covers 4.1 and 4.2 or just one of those? Or
Yeah, I think that it only covers material from 4.1 and it shouldn't cover anything from 4.2.
Okay, thank you.
There is a section about exact differential equations in 3.2. Are we gonna have to know how to do those?
Yeah, if I covered it in chapter 3, I would recommend that you be comfortable with it.
Okay, are we gonna have to know how to parameterize, like change the parameters for equations if they're not like the x equals ln t kind?
No, the only change of variables that we discussed were precisely the Euler equations where the change of parameters is given by x is equal to natural log of t.
Okay.
I won't ask you any equation that requires a change of coordinates that's not that form.
Okay, thank you.
Okay. Any other questions? If not, then I'll kind of discuss what we did yesterday briefly. So essentially at this point, we are done with chapter 4. And the main bullet points that we learned are we have the strong form of existence and uniqueness for higher order linear ODE. Can someone tell me what I mean by the strong form? Well, first of all, what is a higher order, what does an order n linear differential equation look like? Well, I can write it as y to the n plus some function p1 of t, y to the n minus first derivative plus p2 of t times y to the n minus second derivative all the way down to plus pn minus 1 y prime plus pn of t y is equal to g of t, right? This is the general way that we write an order n linear differential equation. Yes? No? Someone say something. Yeah. Okay, great. Thank you. So once we're given a differential equation of this form, a natural question is, given some IVP, given initial data, y at t0 is equal to y0 all the way down to y n minus first at t0 is equal to y n minus 1, 0, right? This is the initial data that would be required. Some point t, or t naught, and some dogs eating flies. Okay, once we have this initial data, we can ask, do we have existence and uniqueness? Of solutions to this IVP. What is the answer? Do we have a theorem which gives us existence and uniqueness?
Yes, as long as all of those p functions in G are continuous on an interval that includes the initial points.
Exactly. This is material from 4.1, so this is material that you should be comfortable with for the midterm tomorrow. We have existence and uniqueness of solutions to IVPs, and the solutions are or can be extended to the largest interval I containing t0 on which all these functions pi of t and g of t are continuous. Right? This is something that you remember, or this is something that you're comfortable with.
Right, yeah.
Okay, great. And then, so this is more or less what we discussed in the first section. We discussed existence and uniqueness, and then we talked about constant coefficient. Constant coefficient, higher order, linear, homogeneous ODEs, right? Just like in the order 2 case, the constant coefficient case is really the only case that we can deal with concretely. And we gave strategies. So if we have R1 through Rn distinct real roots, then we get a general solution C1 e to the R1 t plus all the way up to Cn e to the Rn t, distinct real roots of the characteristic polynomial. And then for complex roots, do as usual. That is, you transform the solution e to the lambda plus I mu of t. This becomes e to the lambda cosine of mu t c1 plus c2 e to the lambda sine of mu t. So these become terms in your big n-term family of solutions. And then for repeated roots, you consider solutions of the form e to the RT, t e to the RT, all the way up to t to the k minus 1 e to the RT if R is a root of order, right? So here we have k linearly independent distinct solutions to the differential equation if the characteristic polynomial has a root of order k. Right? Is this all right?
Yeah.
Okay, maybe I'll just have you do one of these for practice, since we didn't get too much practice yesterday. But I didn't plan on having y'all practice this one, so I'll just essentially make something up. So let's say you factor the characteristic polynomial as x minus 1 cubed times x plus 5 times x minus I plus 1 squared times x minus negative I plus 1 squared. Notice that this will be a polynomial with real coefficients, because for as many times as I have a complex root, I have its complex conjugate as a root as well. So when I take the product of one of these terms and one of these terms, I'll get some sort of real polynomial. So could someone write me down the general solution associated to this characteristic polynomial?
I think I have it.
Okay, so what shall we have?
C1 e to the t plus C2 t e to the t plus C3 t squared e to the t.
Yep, that takes care of these three roots.
And plus C4 e to the negative 5t plus C5 e to the t cosine of t plus C6 e to the t sine of t.
So let me think about this for just a second. The root that we're going to have is e to the I, or 1 plus I times t. Yeah, so e to the t cosine of t, you said?
Yeah.
Uh-huh. Plus
C6 e to the t sine of t plus C7 t e to the t cosine of t.
Yep.
And C8 t e to the t sine of t.
Very good. Did everyone get this?
Mm-hmm.
Okay. If anyone has any questions about how we produce this general solution from this polynomial, you should ask me now, because otherwise I'm going to move on to chapter 7.
I do have one question.
Sure.
When we write it, so she expanded out the c e to the t into the cosines and sines. Is that necessary? Because I guess it wouldn't.
Yes, I would ask that, because there's this general thought that even though we're using complex numbers as an intermediate stage, we want to think of a differential equation as a real differential equation that has real functions as solutions. So we're kind of not thrilled by the idea that we have a complex solution to a real differential equation. And especially in physics, it makes more sense to ask for not just the mathematical function that satisfies the differential equation, but for the real function that could actually describe the equation of motion of some particle, for instance.
Okay, that makes sense.
So yes, I would like for you to expand the complex function in the complex solution into two real linearly independent solutions, which happened in these cases.
Could you explain what happens to the complex conjugate term? Like,
Yeah, right. So as a general rule, we have from having these two roots, we have the following solutions: e to the, in this case, 1 plus I times t, and we also have the roots e to the 1 minus I times t. Okay, and each of these are supposed to produce us two real solutions. The two real solutions here are e to the t cosine of t and e to the t sine of t. And then the two real solutions that I get here are once again e to the t. Here I'll have cosine of negative t, but that's just the same as e to the t cosine of t. And over here, I'll have e to the t sine of negative t, which is the same thing as negative e to the t sine of t. So a priori, what I've got are four real solutions, right? Do you agree that it looks like I have four real solutions?
yes.
Now the next question is, are these four solutions linearly independent?
No.
Definitely not. I have four solutions, but actually there's only a two-dimensional space that's spanned by these four solutions. Namely, once I have one of these two terms, I have the other one because they're literally the same term. And then I can pick up either an e to the t sine of t or a negative e to the t sine of t. But picking up one of these means that I count the negative in terms of my solutions because I'm allowed to multiply by constants, right?
Mm-hmm.
So we see that if we write out all of the real solutions from both a complex solution and its complex conjugate solution, we still only pick up a two-dimensional linearly independent family of real solutions,
Mm-hmm.
either this chunk or this chunk. So in the end, you should only use one of these pairs. Just for convenience and ease of notation, we usually pick the positive complex root and we look at its solutions and then we use those. We could have used these two as well. But the point is, we don't actually get four solutions out of these. We only get two solutions.
Okay, that makes sense.
Does that help with understanding?
Yes, that's perfect.
Great. Right. In some sense, all of the information is carried in just one of the complex conjugates, because the other one is totally determined by this one. Okay, any other questions? These are good questions. No questions? That's all right. You've already asked some good ones. So now we're going to leave all this behind us, more or less. And, well, not totally, but we're going to move on to chapter 7. This is the last chapter that we'll be covering in this course. So, yeah, we've mostly spent our time in chapters 2, chapters 3, a tiny bit in chapter 4, and then we'll spend a lot of time in chapter 7. Okay, and this is systems of ordinary differential equations. And as I try to do, I will try to first explore a motivating example, which just shows you what we would try to write in such a situation. So motivating example. Which is only really motivating if you care about mass springs, but it turns out that mass springs are, first of all, kind of cool, and second of all, the math that is associated with this can be used like everywhere inside math, physics, economics, biology, etc. So we're going to set up a more complicated mass spring system. What we're going to have is we're going to have one mass, and now we're going to introduce a second mass, M2, and these are in some one-dimensional box. And M1 is connected via a spring to the wall. We'll kind of write this coordinate as 0. Then the two masses are connected by a spring, and then M2 is connected to the far wall by a spring. And there's going to be some rest position of this system where nothing is moving. And I'm going to call that rest position, I'm going to denote that distance M1 as L1. So this is L1. I'll call this distance L2. And then I'll call the full length of this one-dimensional box L3. And of course, I have spring constants that I have to remember for each spring. So this will have spring constant K1, and this will be spring constant K2, and this will be spring constant K3. Okay, so if I want to write down differential equations which govern the motion of these two masses if they're displaced from their equilibrium position, then I have to write down two different differential equations, one associated to each mass, right? So I'm going to be using F is equal to ma, but I have to use this twice, one for each mass. So for instance, I would write something like, well, on the easy side is always the mass times acceleration side. So I have mass 1 times the acceleration of the motion describing this first mass, which I'll call x1 double prime of t, right? And let me just write down a priori the forces that are acting on it. I have a force F from spring 1, and then I have a force F from spring 2. Plus, I'll add in another F for some external force. In this sense, the differential equations that we write are the easy part. I just list some forces that seem like they're acting obviously on M1. Only K1 is pulling on M1 and K2 is pulling on M1 from different sides. So we expect these signs to be different. Then we have the second mass times, and then x2 of t is going to be the function which describes the motion of the second mass. So x2 double prime of t. And that's just going to be, well, I'm just going to add up the forces acting on M2. So I'm going to have a force F from spring 2 plus a force F from spring 1 plus some force F for forcing on the second spring. I've really done no math whatsoever. I've just kind of listed the different forces that I want to be acting on my two different masses. Wow, not one, there should be a 3. Spring 3 is acting on them too. Does anyone have any questions just as far as I've written so far? No? Yes? No. If we were in class, I'd tell y'all to do jumping jacks. Dead quiet.
No, this is good.
Great, thank you. I appreciate that. Okay, Hooke's law says that the force given by a spring is linear in terms of the displacement from the equilibrium position. So what we're going to do is we're going to start summing up and totaling all the forces that are involved here. I can do it this way. So I'm going to have M1, let me see if we can get the picture too. So M1 X1 double prime is equal to, let's make the positive direction the right-handed direction. So I'm going to have a particular spring force, and here it's going to be some coefficient times K1. This is the proportional to. If it's proportional to the displacement, that means it's up to a scalar away from the displacement, and that scalar is related to the strength of the spring, so K1. And then what is the displacement of M1 from its rest position? How should I write that?
Just L1.
Well, just L1, if it's just L1, then there shouldn't be any force, right? So it should depend on X1 of t.
Would it be L plus X1 of t?
Well, I want it so that when X is equal to L, then the force is 0. It's neither pushing or pulling when the mass is right here. It's in total equilibrium.
So minus?
So here, yeah, I think I would write X1 minus L1. And then let's kind of figure out the signs. This should be a negative, I believe, and we can check that because if X1 is bigger than L1, that is, if the mass is over here, then the force should be in this direction, or it should be negative because the spring S1 is pulling left on the mass. Whereas if X is less than L1, that is, the mass is over here, then the spring S1 should be pushing. That is, this total number should be positive. So if this is negative, then a negative times a negative will be positive, and it'll be pushing. So I think that this is a correct term to write for the force of spring 1. And then I'm going to write down whatever I get for spring 2, and I'm going to have a similar sort of thing that appears here. So plus, I'm going to have some coefficient times the constant here, K2. And now here, what do I need to be comparing? What is the neutral or rest length of this spring in this system?
Is it L2 minus L1?
Yeah, I want to be comparing something to L2 minus L1. And what is the actual length of this spring depending on X1 and X2? I think it should be X2 minus X1, right? X2 minus X1 measures the actual distance between M2 and M1 at any given point. So x2 minus x1 measures how far away the masses are, and L2 minus L1 is the equilibrium distance when this system isn't moving at all. That's when this spring is at its kind of neutral place. Plus whatever additional force term we have. Are we okay with how I wrote down this differential equation? Oh, we need to figure out the constant here, right? So if x2 minus x1 is larger than this, that is, the distance between these is big, is k1 pushing or pulling? Well, if the two masses are like here and here, then k2 should be pulling the mass 1 to the right. So this should be positive. Okay. Then we just do the same thing for the second mass in the system. Then we'll also write down m2 times x2 double prime. And now I'm just going to write up the sum of the forces from the second spring and the third spring on m2. Here I once again have the exact same term that I had here. I'm going to have a negative k2 times x2 minus x1 minus L2 minus L1. I get the exact same force, like however this spring is acting on M1, it's acting on M2 in the same way, just in the opposite direction. So whatever term I had here, I just replace it over here with a negative sign. And then I add the force that I'm getting from spring 3. Oh, you can't see spring 3 anymore. And then in terms of spring 3, I want some coefficient times K3. And then here I'm looking for, well, the rest distance of this thing is L3 minus L2. And the actual distance of M from the right wall is X2, or is L2 minus X2. Right? L2 minus X2 is this actual distance, and L3 minus L2 is the rest distance. So I want to be comparing those two distances. And then I need to figure out the constant, or what the sign is of K3. So if L2 minus X2 is bigger than L3 minus L2, that means that this mass is over here, right? Because the distance between M2 and the wall is bigger than the rest distance. Then this spring should be pulling on M2 towards the wall. So that's like a positive force, so this should be positive. Plus some forcing if I want it. Now, this is a little more complicated of a system than what we've treated so far, but do you kind of see how what I discussed at the beginning of class is kind of being borne out, that writing down the differential equation or writing down the systems of differential equations is kind of the easy part, in the sense that you're not really doing serious math here. You're just, the only things that go into here are Newton's law, which is F equals ma, and then a bunch of instances of Hooke's law, where it's just telling me how the springs are supposed to behave, how ideal springs are supposed to work. I just did that a bunch of times here. Any questions on this procedure that I did? And of course, this is something that you can simplify. Remember that when I did the mass spring system that looked like this, when I had my mass spring and I said at this length L, we have equilibrium. And then I wrote something like mu double prime is equal to mg minus k times u minus L but then some things simplified, and we ended up getting something like since mg plus kl is equal to 0, what we get out of that is a differential equation, mu double prime is equal to negative ku. We can do the exact same procedure here just by analyzing what happens when m1 is at distance L1 and m2 is at distance L2, and we'll get some simplification of these differential equations. So this isn't exactly what appears in the book, but you can get what appears in the book by simplifying these equations, and the way that you simplify them is by writing down what equations you get for the stable term, where x1 is equal to L1 and x2 is equal to L2, and then all the forces cancel out because there's no motion. Is it clear what I just said?
Yeah.
Yeah.
Okay, so this is an example. This is an example of a system of differential equations. In particular, let's ask, first of all, are these differential equations, what is the order of these differential equations?
Second order?
Yep, both of these are second order because they involve a second derivative somewhere. Are these linear equations?
Yeah.
Yeah, these are all linear differential equations because at the end of the day, when I multiply everything out, I'm only going to have constants times the zeroth derivatives of the xi's, and there are no first derivatives appearing. So this is a system of second order linear differential equations. And these are the problems that you've seen now how they can arise naturally in physics. These are the problems that we want to start solving. Right, that's what we want to start solving now. Okay. I want to, let's see, what do I want to say first? So here's a comment that I want to introduce. And this is a very interesting comment and perhaps provides a motivation for why systems of differential equations are so valuable to study. We can transform higher order differential equations into systems of differential equations. Essentially, this procedure happens by renaming the variables that you're using. So just to do an example, if we have some higher order, in this case, second order differential equation, u double prime plus 1/8 of u prime plus u is equal to 0, then we essentially make a, I hesitate to call this a change of variables, but that's one way to think about it. What I do is I make a function x1 and I just call it equal to u. And then I make a new function x2 and I call that u prime. And then if I substitute in for this differential equation, I get the following collection of differential equations involving my new variables x1 and x2. I get the following system. I get x1 prime is equal to x2. This is just reflecting the fact that the derivative of my first variable is equal to my second variable. That's how I set it up. And then x2 prime, which is, as we know, equal to u double prime, what is that equal to according to this differential equation?
Would that be 1/8 x2 plus x1?
We'll pick up negatives, but
Negative.
essentially, yes. It'll be negative 1/8 times x2 minus x1. So what we have done here is we have transformed a second order linear differential equation into a system of two first order linear differential equations, right? Here, the highest derivatives that appear are first order derivatives. Now, on one hand, this gives us some hope because first order linear differential equations are the things that we can actually literally solve every time, right? We had the most control over the solutions when we were dealing with first order linear differential equations. So perhaps we can say, aha, maybe we have made progress on this problem. The downside, or the fact that maybe suggests that we haven't actually made progress on the problem and we've just transformed it into a new difficult problem, is the fact that now our differential equations involve several functions. In particular, the derivative of the first function is equal to the second function, and the derivative of the second function involves both of the original functions, x1 and x2. So a priori, it's unclear whether we've actually done ourselves a favor here, but at least it's important to notice that we can always use this trick to perform higher order differential equations into systems of first order differential equations. Why don't I give y'all one for practice? So transform the following differential equation into a system of first order differential equations. Let's do u triple prime plus u double prime times u prime plus u is equal to 0. Notice that this is not a linear differential equation. And so I don't expect to get linear first order differential equations out of it. So why don't you work on this for a little bit?
Sorry, are we going to expect one or two or three equations because it's a third order differential equation?
You'll need, if you want a system of first order, then you'll need 3 variables, namely x1, x2, and x3.
Okay, thank you.
Yep. I'll be right back. Okay, does anyone have the system of differential equations for me? So I want differential equations relating the first derivatives of each of my functions. So first of all, what should x1 be equal to?
x2 prime? Or, no, sorry,
Just u.
u.
Yeah, it should just be u. And then I'm going to set x2 to be equal to u prime. And then I'm going to set x3 to be equal to u double prime. Right? This is a reasonable choice to make. And then now, once I've made this choice, I can write down differential equations. X1 prime is going to be equal to what?
X2.
X2.
Yep, x2, because u prime is equal to u prime. X2 prime, the derivative of u prime, is going to be equal to
X3.
x3, good. And x3 prime is going to be equal to, well, that's the same as u triple prime, and that's going to be equal to what?
Negative X3 minus X2 minus X1.
Negative 3 times x2 minus x1. Right? All I did there was I moved this term to the other side, and I can rewrite everything in here in terms of my functions. So now I have a system of 3 first-order differential equations, 2 of which are linear and 1 of which is nonlinear. Okay? Any questions on this procedure?
I don't understand how you got x3 prime.
So x3 prime, so if x3 is equal to u double prime, then x3 prime is equal to what? In terms of u.
U triple prime.
U triple prime, exactly. Now remember that we started with this equation. U triple prime plus u double prime plus u times u prime plus u is equal to 0. Or if I do some algebra, this is the same thing as u triple prime is equal to negative u double prime u prime minus u.
Oh, I get it. Thank you.
That's exactly what I did here.
Yep.
So what's the point of like renaming all the u's into x's? Because couldn't you just write the system with just u's instead?
Right, that's what we did here. So what I'm, sorry, go on.
No, that was it.
So here's what I would say is that in a certain sense, we're broaching an even wider class of problems. So the collection of systems of differential equations strictly contains the class of differential equations, right? What I'm showing you here is how you can pass from a higher order differential equation to a system of differential equations where all of the differential equations are first order. It's just something to be aware of. So this tells you that maybe instead of spending all your time working on higher order differential equations, maybe you should develop some tools to deal with systems of first order differential equations, and then anything you prove there will give you progress on the higher order problems that you might care about. Does that make sense?
Yeah, makes sense.
So, and in particular, here's the following note. So more generally, we are going to write the following. So a system of first order differential equations is the following. Say x1 prime is equal to f1, and this is going to depend on t x1 all the way up through xn. And then x2 prime is going to be some function f2 time, and f2 is a function of t, x1 all the way up through xn, all the way down to xn prime, which is going to be equal to fn, and fn is in terms of t, x1 all the way up through xn. So this is kind of the most general form of a system of first order differential equations. And I made no comment that these are first order linear, so these are just arbitrary functions depending on these variables. Notice that in the previous examples that I did, the first n-1 functions were very simple. When you translate a higher order differential equation to a system, then x1 prime is equal to x2, x2 prime is equal to x3, x3 prime is equal to x4, etc. And it's only xn prime that is a complicated function. Here, I'm reintroducing some generality into this world of systems of differential equations. Okay, some basic questions. What is a solution? To a system of differential equations. What should it mean to have a solution to this differential equation, or the system of differential equations?
You found the functions x1 through xn?
Yeah. A system, or a solution, is a collection of functions x1 of t, x2 of t, x3 of t, etc., all the way up through xn of t, such that this collection of functions all satisfy all the differential equations that you require them to satisfy. What should we ask for initial data? Remember that every time that we talk about solutions to differential equations, we have the impression that solutions are not unique until you specify a required amount of initial data. What does initial data look like for a system of first order linear, or not linear, first order differential equations? Does anyone have a guess for how many pieces of data we should be asking for?
N?
Yeah, we should be looking for n pieces of data. And in this case, what we want to pick is a starting time, t0, and the data of, well, x1 at t0 should be some x0. This is telling you what this actual function is as a function of time. Remember that if I find one, well, I'll get to that later. But yes, what I should be expecting is, sorry, I'll write it lower x1, upper 0 for some number, which is some initial data. X2 at t0 should be equal to x2 naught, all the way up to xn at t0 should be equal to xn naught. So really, this is something very reasonable. If I'm dealing with a first order linear differential equation, a solution, to specify the IVP, all I need to tell you was where that, how high that function is at a particular point. And that's enough to specify it. Well, if I've got a whole bunch of first order differential equations, probably I just need to specify the height or the value of all those functions at a given time. And then that should be enough to determine a unique solution. And indeed, we have the following theorem, which I will not prove, but you can guess what it's going to be. It's going to be an existence and uniqueness theorem. So theorem. Existence and uniqueness. Let x1 prime is equal to f1 of t comma x1 all the way up through xn. x2 prime is equal to f2 as a function of t, x1 all the way up through xn, all the way down to xn prime being equal to fn as a function of t, x1 all the way up through xn, be a nth order or a system of n first order differential equations. So we assume all partials, or sorry, all functions f, all these functions on the right-hand side, and all partials fi, the partial derivative of fi with respect to xj, here for all I and j. So remember, all these functions f1 through fn depend on both time and potentially all of the variables. So I need to take all of the possible partials. I need to take the partial of f1 with respect to x1. I need to take the partial of f1 with respect to x2, all the way up to xn. And then I need to repeat that process with every function. So I need to take the partial of fn with respect to x1, take the partial of fn with respect to x2, etc. If all the fi and all the partials partial of fi with respect to xj for all xj are continuous on a rectangle, really this is a generalized rectangle, right? It's in many dimensions. It's in n+1 dimensions, containing the initial data t0, x1 naught, all the way up through xn naught, then there exists a unique solution to the system, or to the IVP, on some smaller generalized rectangle. Or on some interval, essentially. Smaller interval in t. Around t0. So, okay, I just wrote down a huge amount of symbols and words. Any questions before I discuss this existence and uniqueness theorem a little bit? Any questions on handwriting, for instance, or what did I write there, or such and such?
This would be an example of something that's not a strong existence
That's
theorem.
correct. That's correct. So that's a very good comment. So first of all, I didn't make any assumption that these are first order linear. These functions fi could potentially contain products or cosines or whatever involving the xi's and xj's, in which case they are nonlinear. And we remember from chapter 2 that the moment that we passed to nonlinear differential equations, even if they were first order, all of that, the moment that we have nonlinear differential equations, there were two things that we needed to do for the existence and uniqueness. First of all, we had to check both of the functions and the partials. And once we had done that, we only got existence and uniqueness on a small interval around t0. We don't get a big interval where you have existence and uniqueness of a solution. You're only guaranteed it on some small interval around t0. That's exactly the same sort of thing that we're getting here. When we have some first order nonlinear system of differential equations, first you have to check continuity of all the functions and all the partials. And they have to be continuous on some generalized rectangle containing the initial data. And once you're continuous on all of these, or once you have all of this huge number of functions continuous on some small rectangle containing your initial data, then you're guaranteed existence and uniqueness on some even smaller set. Namely, you're just allowed to take some small interval around t0 where you can write functions x1, x2, all the way up through xn, depending only on t. So in a certain sense, this is not so unexpected from what we saw for existence and uniqueness in chapters 2 and 3 on nonlinear differential equations. It's just now you have to check a ton of functions and a ton of partials. Any questions here? Yes? No? Okay, that's all right. The problems that we will deal with, so you can probably expect this. I'm starting to sound like a broken record, but hopefully this gives cohesiveness to the class. Nonlinear differential equations are too hard for us. In fact, nonlinear differential equations have been too hard in almost every case, except briefly in chapter 2, when we spoke a little bit about separable differential equations and exact differential equations. Separable and exact differential equations are, to my knowledge, the only time that we've been able to treat nonlinear differential equations. So what we're going to go back to is systems of first order linear differential equations. Right? This is expected by all. Okay. So what does it mean for me to have a system of n first order linear differential equations? Well, I've got some function, a collection of functions, x1 through xn, and then I need to specify some relations on their derivatives. x1 prime is going to be some stuff, x2 prime, all the way up to xn prime. What should x1 prime be equal to if I'm asking for a linear differential equation in terms of the functions x1 through xn?
P1 of t times t plus P2 of t times x1 and so on.
I'm going to give P1 the extra notation of 1, 1, but you're right. I want some function of t, which I'll call P11 of t times x1, plus P12 of t times x2, plus all the way up to P1n of t xn, plus g1 of t. Right? Here are, I just want coefficients in front of each of the functions that only depends on t. This is some function only depending on t, only depending on t. And at the very end, I'm allowed to add some function which is only depending on t. And similarly, here, I'm going to have P21t times x1 plus P22t times x2 plus all the way up through P2n of t xn plus g2 of t. And I repeat this whole system all the way down to the bottom, where here I've got Pn, comma 1 of t times x1 plus Pn 2 t times x2, all the way up through Pnn of t times xn plus gn of t. Okay. Is this understandable, right? So now the two coefficient, or not the two coefficients, the two indices under the functions t. The first one refers to the row you're in, and the second one refers to the column. So P21 is in the second row and the first column, and P34 is in the third row and the fourth column. So those of you who have seen some linear algebra are starting to have flashbacks, hopefully. Okay, what should our definition of a homogeneous system be? What would make all of these linear equations homogeneous?
All the g functions are 0.
Exactly. A homogeneous system is when gi of t is equal to 0 for all I. And then what you're left with is literally n different equations, where on the left side I have a first derivative of one of the functions, and then it's written in terms of the other functions with coefficients being functions of t. So we see that this nomenclature is very reasonable. Any questions here? And we'll see that a lot of the stuff that we know about linear differential equations transfers over to the world of systems of linear differential equations. For instance, when we have a system of linear differential equations, then we have theorem, here's existence and uniqueness, for systems of linear differential equations. First of all, if the Pij and the GL for all I, J, and L are continuous on an open interval, let's call it I with T naught contained in I, right? So some open interval containing my initial time, then have existence and uniqueness of solutions to the IVP given by this differential equation, given by the diffeq plus x1 naught, x2 naught, all the way up through xn naught, and solutions, oh, sorry, I'm writing too far down, exist on the largest interval on which all functions Pij and GL are continuous. So in other words, the moment that you add the restriction that you're dealing with systems of linear differential equations, then once again we recover a strong form of existence and uniqueness, where all you need to check are continuity of the functions that are involved, namely these coefficient functions Pij and the non-homogeneous pieces GL of t. And if all of those functions are continuous on some big interval, then you can define solutions, namely you have a collection x1 of t all the way up through xn of t, this is a solution to the IVP, and it's defined on I, where I is any interval on which all these things are continuous. So once again, the moment that we pass back to linear, we recover a strong form of the existence and uniqueness.
Does that operator next to where you wrote interval I, does that just mean I includes T0?
Yeah, that means T0 is included inside the interval I. Yep.
Thank you.
Any questions about this? I feel like this is not a surprise, really, or at least this is what one would hope for and what one would kind of expect, right? Hopefully you leave this class appreciating the difference between linear and nonlinear differential equations in all their forms. Any questions? Okay. Let's examine the following. I'd like for you to work out this other example, which should be kind of a flashback from something that we discussed in the previous section. Why don't you work out the following? So let the tuple x1, y1 and x2, y2 be two solutions to x1 prime is equal to p11 x1, or sorry, x plus p12 y plus g1 of t, and let, sorry, this shouldn't have this, and y prime is equal to p21 x plus p22 y plus g2 of t. Show that x1 minus x2 and y1 minus y2, this is a new pair of functions, which is possibly a solution to this differential equation, possibly not, is a solution to the homogeneous system. Where here, homogeneous system means that I set G1 to be 0 and I set G2 to be 0. So why don't you try to work this out? And this looks almost exactly like an equation that I wrote when we were passing from solving second order linear differential equations to solving non-homogeneous second order linear differential equations. We had this exact same relationship where the difference of two solutions to the non-homogeneous equation gives us a solution to the homogeneous equation. Does everyone understand what they're trying to show?
Yeah.
Yes.
Cool. So just to write down what you're trying to show that if you plug in x1 minus x2 and y1 minus y2 into two sides, one, you either plug it into x prime and y prime. So x prime is the derivative of this component, and y prime is the derivative of this component. And you want to check that that's equal to p11 times x1 minus x2 plus p12 times x1 minus x2. I'm running out of space. And similarly on this side, you want to check that when you take the derivative of y1 minus y2, you want to check that that's equal to p21 of times x1 minus x2 plus p22 times y1 minus y2, right?
Yeah.
And this is more or less easy. It's just repeating the exact same argument that we did back in when you weren't dealing with systems of equations. Namely, if we have the tuple x1 minus x2, y1 minus y2, then x prime is equal to x1 prime minus x2 prime because derivatives are linear. And we already know that x1 comma y1 solves the differential equation, and x2 y2 solves the differential equation, or solves the system. So in particular, what is x1 prime? From the fact that we're solving this differential equation, what is x1 prime?
P11 times x1.
Yeah. P11 times x1 plus P12 x, or what is it, y1 plus g1 of t minus, and now here I get whatever x2 is, which is P11 of x2 plus P12 of y2 plus g1 of t. And this whole thing simplifies out to P1, the g of t, g1 of t and the g1 of t will cancel over here, and I'll get P11 of x1 minus x2 plus P12 of y1 minus y2. And this shows that the first of the two equations is indeed satisfied, right? This says that this tuple satisfies the homogeneous piece of the system x prime is equal to P11 of x plus P12 of y. And then the second equation is essentially the exact same thing. Does anyone have any questions about what I'm doing here or what I've done so far? Should I finish this problem?
It seems good. Just a quick question. Would it be
Sure.
important to add the g of t to the end?
You
Or
mean
is that-
here?
Yeah.
It doesn't belong here. In fact, it's very important that it's not here. The point is that the g of t here cancels out with the g of t here. So just like what we discussed in the back in the other stuff, this set of solutions to a non-homogeneous differential equation don't form a vector space. In particular, x1 minus x2, y1 minus y2 is not a solution to this differential equation. It's only a solution to the homogeneous system where the g's vanish. And that's exactly what we see here.
Okay.
When I take the derivative of this term, I get this minus this. The g1s cancel, so this looks like it's going to be the solution to the homogeneous piece of this system of differential equations, where there is no g1 here. That's the point.
So this doesn't apply to non-homogeneous systems.
This is the analogy, remember, that we had. So say that we have y double prime plus p of t y prime plus q of t y.
Oh, I see what you
And
mean.
equals g of t. If L of y1 is equal to g of t and L of y2 is equal to g of t, then that means y1 and y2 are solutions to this non-homogeneous differential equation. Then L of y1 minus y2, is this going to be a solution to this non-homogeneous differential equation?
No, just the homogeneous part.
No, it'll be equal to 0, so that tells you that y1 minus y2 is a solution to y double prime plus p of t y prime plus q of t y is equal to 0, right? So if you take two solutions to the non-homogeneous and you subtract them from each other, you get a solution to the associated homogeneous. That's
Okay.
exactly what we see here. We take two solutions to the non-homogeneous system, and we show that if we subtract these solutions from each other coordinate-wise to get the function x1 minus x2, y1 minus y2, this pair of functions, then this pair of functions solves the associated homogeneous linear system.
Okay.
Good question. Yeah, that's an important thing that I wanted to clarify. We don't get solutions to the non-homogeneous thing. We only get solutions to the homogeneous thing. But that's what we expect from our second-order non-homogeneous discussion. Any other questions on this? No? Well, in that case, I'm probably just going to end class a little early today because I'm not about to start 7.2, which is just a gigantic amount of matrix computations and matrix manipulations. It will not feel at all like differential equations. It'll feel just like linear algebra and just like matrix mechanics for probably almost all of Thursday. So there's no reason for me to start that now. What do I want to say? I just want to point out why we're going to be doing a ton of matrix mechanics. And the answer is this. The data, all of the data of this, let's pretend that we're looking at a homogeneous differential equation. All that we need to rebuild this system of linear differential equations, which are homogeneous, is the data of an n by n array where each element in the array is a function of t. So this is exactly the same thing as a matrix, an n by n matrix, where all of the entries are functions of t. So just from this picture right here, you can already see where matrices are going to appear. What we're going to spend Thursday doing is discussing some basics of matrices so that we're all on the same page in terms of adding them, multiplying them, whatever. And then we'll apply that to solving these systems of differential equations. Okay. All right. Have a nice afternoon. And good luck on the test tomorrow. See y'all at 11:30.
Do we take a video of ourselves taking the test, or are we doing the Zoom meeting again?
If you're in a time zone that is within 1 or 2 time zones from class time, then you should turn on your Zoom. If you're in a time zone that means that you cannot take the test at the 11:30 time period, then you must take a video of yourself.
Okay, thank you.
Thank you.
Thank you.
Yep.
Thank you.
All right. See y'all tomorrow.